Welcome to this explainer. Let's dive straight into a truly thrilling mathematical detective story. Today, we're connecting the highly abstract Adelic Langlands Program to the literal stability of spacetime itself.
We've got some intense equations ahead, but here is our logical roadmap. First, the phase complexity barrier, followed by the Adelic pipeline proof. Then we'll cover semi-classical boundary collapse, Rankin-Selberg entanglement, gravity as saturated mass, and finally, the cosmic hardware.
Section 1. The phase complexity barrier.
To understand the fundamental threat to the stability of the universe, we really have to look at polylogarithms. As the integer index m in these classical equations scales up, these functions create what is basically a path integral labyrinth. Imagine infinite, overlapping sheets of reality. We call these branch-cut singularities, just stacking up and generating this totally unmanageable, chaotic noise right on the complex plane.
Think about classical continuous chaos with its infinite ambiguities in continuous Archimedean domains, the smooth space we're used to. Now compare that to the Adelic solution, which acts like a massive digital filter. It uses discrete p-adic math to literally snap values into rigid fractal-like structures on a Brouhat-Titz tree. This creates a perfectly clean, unramified baseline. It's a total game changer for stabilizing that chaotic noise.
Section 2. The Adelic pipeline proof.
So how exactly do we solve this infinite chaos? We use a brilliant three-step mathematical machine called the Adelic pipeline. First, we start with a highly complex, higher-weight element in the generalized block group. Second, we apply the Grothendieck-Riemann-Roch push-forward, which is essentially a mathematical translation tool. And third, we lift this into a continuous Galois representation. This pipeline actually untangles those chaotic branching paths, allowing us to perfectly track the arithmetic singularities.
Following this system architecture, we inject those higher block group elements straight down through the Dirac operator into Adelic space. From there, Satake regularization kicks in as a stabilizer, compelling a lift to the Langlands dual group. Ultimately, this integration forces a complete cosmic boundary collapse.
The mathematical heart of this Satake regularization is the L function equation. Think of it as our cosmic digital filter. The local p-adic factors in the matrix take all those chaotic, continuous waves and compress them down into a smooth, manageable degree n polynomial. J-theory actually demands complete stability here, filtering out all the ambient noise to leave just a pure, unramified baseline.
Section 3. Semi-classical boundary collapse.
It's basically a mathematical seesaw. The global functional equation forces the high-energy spectral weight to perfectly balance the deep, discrete arithmetic core. It's a strict mirror symmetry. The universe absolutely demands that the total informational budget of the logos field remains perfectly conserved across this critical mirror axis. And there's an exact formula enforcing this balance. By equating the discrete global partition function to the continuous regulator volume, this identity rigidly clamps the global conductor anomaly strictly to n equals 1. In physics, n equals 1 literally means zero chaos. It collapses all phase ambiguities onto a single, perfect orbit, definitively proving Goncharov's exact ratio.
The absolute crucial takeaway here is this conservation law. The total informational budget of the logos field must remain perfectly conserved across the mirror axis. If any non-trivial winding anomaly were to break this balance, well, it would drive up the cross-entropy of the vacuum, effectively dissolving our universe into infinite quantum noise. Not exactly an ideal scenario.
Section 4. Rankin-Selberg entanglement.
Now, what happens when two independent high-frequency vacuum fields crash into each other? The Rankin-Selberg convolution equation computes exactly that. The local L factor equation tracks the internal eigenvalues, represented by alpha and beta, of these two distinct fields, mathematically mapping their cross-channel information exchange over a discrete unit disk.
The cross-entropy of these two competing fields is strictly regulated by the prime numbers anchoring the center. The fields simply cannot intertwine with arbitrary mismatches. This strict Rankin-Selberg limit prevents divergent energy from tearing the vacuum apart and instantly forces the four-dimensional spacetime metric to stabilize. It's essentially an arithmetic squeezing mechanism.
Section 5. Gravity as saturated mass.
Prepare for a massive aha moment. When we map the arithmetic stress factor equation, which measures the internal pressure of non-commuting phases, that exact pressure maps flawlessly to the emergent 4D Ricci curvature tensor. The foundational math of Einstein's general relativity. This absolutely proves that gravitational curvature is literally generated to absorb non-abelian stress. Matter itself is just maximally compressed higher-frequency data. Mind-blowing, right?
Section 6. The cosmic hardware.
Those polylogarithmic branch structures we talked about earlier, they actually serve as the physical hardware for fault-tolerant logical qubits. The physical qubit array acts as a generalized topological quantum code, complete with localized parity checks generated by boundary operators. The universe is essentially structured like a flawless motivic quantum computer.
Which brings us to the Satake-Movic syndrome operator, basically the universe's multi-qubit measurement circuit. If the determinant equation reads an eigenvalue, lambda, of exactly 1, the baseline is totally safe. But if lambda is anything other than 1, it flags a physical phase slip error. That means a local mismatch has occurred right in the fabric of spacetime.
So what happens when that error is flagged? The very moment a phase slip is detected at a specific prime coordinate, the global L function immediately integrates and clamps the conductor back to n equals 1. It operates with absolute fault tolerance, mathematically crushing those phase deviations and returning the entire system back to an unramified orbit. The Adelic motivic code invariant is the explicit mathematical proof that our universe remains structurally stable. The cosmos is actively running a quantum error-correcting routine anchored to rigid absolute number-theoretic invariants across the prime network topology.
To summarize this entire incredible journey, the smooth geometric space and physical laws we experience every day are simply the active runtime display of this absolutely unified, discrete, error-correcting Adelic information network running underneath it all. Motivic rigidity quite literally equals error correction.
As we wrap up this explainer, I'll leave you with this mind-bending thought to ponder. If our universe is actively running a motivic error-correcting routine at its most fundamental mathematical level, who or what wrote the code? Thank you so much for exploring this absolutely fascinating framework with me.